to class. We are now in module 2, standard electrode potentials. We are going to be looking at electromotive force, standard after electromotive force, standard electrode potentials. We look at standard hydrogen electrode She. Look at determination of standard electrode potentials using standard hydrogen electrode. We look at how we can represent cells, that's representation of cells. We look at other standard electrodes. Apart from standard hydrogen electrodes, there are also other standard electrodes, and we'll conclude. Electromotive force. Now when we talk about EMF, that is the voltage of any cell, EMF. So which means that EMF is the potential difference of a cell measured at equilibrium. And when we say equilibrium is when no current is flowing and between platinum terminals. So that is what we call EMF. A more simple approach is to interpret EMF in terms of the difference in electrode potentials of two electrodes. Remember, when we look at the Daniell cell, we have two electrodes, the zinc electrode and the copper electrode. And we said that the EMF of that Daniell cell is 1.10 volts. So we're talking about, we can also talk about electrode potential or electromotive force between two electrodes. And that means that the EMF of a cell is given by E right minus E left, equation 1 there. That is electrode potential of the electrode on the right minus the electrode potential of the electrode on the left. If you look at the Daniell cell, our zinc electrode is on the left and our copper electrode is on the right. And that's why we have that potential. So where E subscript R is electrode potential for the right hand electrode and E subscript L is electrode potential for the left hand electrode. Now, because of this E right and E left we are talking about, we have a convention. So by convention, the anode is kept on the left and the cathode is kept on the right for galvanic cells. Like the Daniell cell, the anode is where you have the zinc electrode, that is the anode, where the oxidation takes place, whereas the cathode is on the right, the copper electrode, where we have reduction of copper or copper ion. So following this galvanic cell convention, that's why we have E right minus E left. We'll also see some other definitions of electromotive force, just like when we talk about E oxidation minus E reduction. Standard electrode potentials. Electrode potential, that is EMF of a single electrode, is not measurable. Now you see, you can't measure that of a single electrode. We'll see why, and we'll also see how we'll measure the standard electrodes of all other single electrodes. The EMF, which is actually relative EMF of any electrode, is determined with the choosing standard electrode. The hydrogen electrode is usually chosen as a reference standard electrode. The hydrogen electrode is the standard hydrogen electrode, which I said we call SHE, SHE. That is what is chosen as a reference standard electrode. The key to using this reference point is recognizing that the overall cell potential for a reaction must be the sum of the potentials of the oxidation and the reduction half reactions. So we can see that for us to talk about standard electrode potential or EMF, electromotive force of a cell, we're talking about the sum of the potentials of the two half cells. And that's why we're using the hydrogen electrode, the standard hydrogen electrode, as our standard reference electrode. There are other electrodes that are also in use, but the original thing that we started with is a standard hydrogen electrode. We'll still mention some other electrodes that can be used. Now, in the Daniel cell, remember, the zinc loses electron, that is, it oxidizes with a driving force that exceeds the resistance acceptance of electron by the copper ions. The copper is reduced. So copper undergoes reduction, zinc undergoes oxidation. The driving force with which metals lose electrons is measured as standard electrode potentials. Standard electrode potential is defined as the potential difference between a standard hydrogen electrode and a metal which is immersed in a solution containing metal ions at molar concentration at 25 degrees C. So we're talking about standard now because we have conditions where we talk that these things are under standard conditions. For instance, the concentrations of the metal ions must be 1 molar and the temperature must be 25 degrees C or 298 Kelvin. So you can see in the Daniel cell, we have a standard electrode potential for the zinc electrode or the zinc half reaction. We also have the standard electrode potential for the copper half reaction. So when we couple the two to make up the Daniel cell, we now have that standard reduction potential for the Daniel cell. Now, the cell potential for a voltaic cell is the potential of the cell to do work on its surrounding by driving an electric current through a wire. Remember that once the zinc dissolves in the Daniel cell and gives out electron, the electron is transported through the wire in the external circuit and goes to the cathode where the copper ions, accept those electrons to become copper metal. So we're saying that it is a potential that is for that cell to be able to do work on its surrounding. By doing work on its surrounding, it is driving an electric current through a wire. By definition, 1 joule of energy is produced when 1 coulomb of electric charge is transported across a potential of 1 volt. Remember when we talked about our units and definitions in the earlier module, we said that 1 joule of energy is equal to 1 coulomb of charge multiplied by potential of 1 volt. And still remember that 1 coulomb of charge, which is Q, is equal to current times time. Therefore, we have E overall, that is E for the cell, will be E oxidation plus E reduction. Now remember, you should be able to know that the oxidation is kept on the left and the reduction half cell is kept on the right by convention for our galvanic cells. Now, SHE consists of a platinum electrode immersed in a 1 molar solution of hydrogen ions, maintained at 25 degrees C and 760 millimeter mercury. That's 1 atmospheric pressure. Hydrogen gas at 1 atmospheric pressure is bubbled over electrode and passes into the solution, forming hydrogen ions and electrons. Look at the half reaction. That's equation 3. Is a half reaction for the hydrogen, standard hydrogen electrode. Now, the EMF corresponding to this electrode, that is equation 3, is arbitrarily assigned a value of 0. So you see why we say it is a reference electrode. The EMF is assigned 0. So we'll see that some half cells will have positive values, while some half cells will have negative values. In fact, this leads to, we don't want to get to you, but we'll mention that the activity series. Just take your time. Google activity series. When you Google activity series, you will now see where all the standard half reactions are listed. And you see the half reactions that are above hydrogen and see the half reactions that are below hydrogen. And you see that the EMF or standard electrode potential of the hydrogen electrode is assigned a value of 0.00 volts. And that value of 0.00 volts is what is used in reference to those standard half electrodes that can force hydrogen to get oxidized and those standard hydrogen electrodes that cannot force hydrogen to get oxidized. Or in the other way, is a measure of the oxidation power and the reducing power of any electrode. So EMF values under standard conditions are known as standard electrode potentials or standard reduction potentials, and we designate them as E naught values. That's E superscript 0. That's what we mean by standard reduction or standard electrode potentials, standard reduction potentials. It means the same thing. The standard electrode potentials of an electrode is given a positive value if this electrode is more positive than the standard hydrogen electrode. So if it is more positive, it is given a positive value. And on the other hand, a negative value is assigned when it is more negative than the standard hydrogen electrode. So you see, like I said in the activity series, you see those that have positive values that are more positive than the hydrogen electrode, and those that have negative values that are more negative than the hydrogen electrode. And the standard hydrogen electrode itself will be at the middle of 0.00 volts. Now this is the standard hydrogen electrode. You can see, remember we said hydrogen gas is bubbled. Look at it, top right here. Hydrogen gas at 1 atmospheric pressure, enters in here. Look at the bubbles down here. This is platinum, platinized platinum foil, the vessel containing it, then a solution of hydrogen ions, 1 molar, and this setup is what we call standard hydrogen electrode. Determination of standard electrode potential. Remember we said that the standard hydrogen electrode, excuse me, we said that the standard hydrogen electrode is used for determination of standard electrode potential. Now, the cell, next slide, we will see, next slide, is a voltaic cell in which a standard hydrogen electrode is combined with a zinc electrode, which is immersed in 1 molar solution of zinc ion. Now, we'll see that equation 4 gives us the combination. We'll also see representation of cells. This is an example of representation of cell. The left-hand electrode and the right-hand electrode, separated by double slanted lines, which is the salt bridge, or also can represent a porous partition. The electrodes, that is metal and hydrogen, are connected through a voltmeter, and the solutions are joined by means of a salt bridge, which is usually KCl. Now, the standard electrode potential of zinc is minus 0.76 volts, and that is so when the potential of standard hydrogen electrode is 0. So zinc is more negative. The reaction taking place at the left electrode is oxidation reaction, and that taking place at the right hand electrode is reduction reaction. The cell reaction is the sum of the two reactions. So we can see this equation 4. Let's look at what is happening in the diagram. Next slide. Now look at what we're saying. Look at zinc. Zinc oxidizes, releasing 2 electrons, which flows through the external circuit. In fact, this is almost the same thing with the Daniel cell, except that the copper right-hand electrode is now replaced by the standard hydrogen electrode. And you can see the connection. But again, the difference here is that the standard hydrogen electrode there is assigned a value of 0.00 volts. And the potential that results in this connection is minus 0.76 volts. And that is the potential, the standard hydrogen electrode of this zinc electrode. Assuming we can also remove this zinc and put something like copper, then we'll see that when copper is here, instead of hydrogen being reduced, hydrogen will be oxidized. So copper will now be on the right hand side, while hydrogen electrode will be on the left hand side, and we'll get a value, a positive value for the EMF, which is for the copper electrode. So that is how these standard electrodes of all these half reactions are measured and tabulated. Like I said, if you look at the activity series, you will see the standard electrode potentials. They are listed and documented. Representation of tiles. Now, so we are talking about, okay, let's take a cell of zinc electrode coupled with a standard hydrogen electrode. That is what we have just seen in the last slide. And we'll see zinc and hydrogen. So the IUPAC convention requires that the positive electrode should appear on the right of this diagram, while the zinc electrode should be on the left. Zinc is a negative electrode because with the standard hydrogen electrode, the EMF is minus 0.76. Now that means EMF is E right minus E left, which we met before. Similarly, for the cell coupled by copper and standard hydrogen electrode, yes, that's what I said. You now see an exchange. The standard hydrogen electrode is now on the left and the copper is on the right. So you see the half reactions. And then, of course, for the Daniel cell, which we looked at before, zinc is on the left, copper is on the right. And that's why we have the E cell for the Daniel cell as E right minus E left. So we have 0.34 minus 0.76, which gives us 1.10 volts. So the EMF of a cell for standard conditions, we have said that the temperature, concentration, temperature must be 298 Kelvin or 25 degrees. And of course, the pressure must be 1 atmosphere or 760 millimeter mercury. So we're saying that we can now do this by subtracting the more negative from the more positive. If you look at the last equation, E right minus E left, if you follow the convention, that's exactly what we have done here. The other standard electrodes includes one standard silver chloride electrode. Remember, the first one is C, standard hydrogen electrode. Now we see that here silver electrode is in contact with solid silver chloride, which is slightly insoluble, which is highly insoluble salt. The whole setup is immersed in KCl solution, in which chloride ion concentration is 1 molar. You can see the equation as equation 5 here. Now for a cell involving this electrode and hydrogen electrode, remember this left hand side is already our hydrogen electrode, oxidation of hydrogen to hydrogen ion, and then for us now is silver chloride and silver chloride, which is 1 molar, that is potassium chloride, which is 1 molar solution, supplies this chloride here. So this right hand side here is 1/2 cell, this is another 1/2 cell, and by our representation of cells, these two slanted line here shows that there's a salt bridge. Okay, we said here with a salt bridge connecting the two solutions. And the EMF of this cell is 0.224 volts. Look at the half reactions. This is a half reaction for the left hand electrode. This is a half reaction for the right hand electrode. And this is the overall half reaction for the standard silver chloride electrode. The next is the calomel electrode. That's the second one, the other type of electrode. And here we have mercurial chloride immersed in 1 molar solution of potassium chloride. Now look at the same thing again. This is a complete cell. By the left hand side, you have the standard hydrogen electrode. Now on the right hand side, we have the mercurial chloride electrode. And these are the half reactions, the hydrogen electrode again, and here is the mercurial chloride, and when we combine the two, we have equation 11, which is the general reaction for the calomel electrode. The EMF of this cell at room temperature, that's 25 degrees C, is 0.3338 volts, which is the standard electrode potential for this cell. Now what that means is that we can use the calomel electrode in place of the hydrogen electrode. Remember, the EMF of the hydrogen electrode is arbitrarily assigned to be 0.00 volts, as we said earlier. So but now, because of the bulky hydrogen cylinder that is needed for the standard hydrogen electrode, we can use the calomel electrode in place of the standard hydrogen electrode. And on the right hand side here, we'll see a sketch, a diagram of the calomel electrode. And the third type of the electrode is a glass electrode. Look at the diagram of the glass electrode. In its simplest form, the glass electrode consists of a tube terminating in a thin wall glass bulb. The glass bulb being reasonably permeable to ions, that is ions, reasonable permeability to the ions. The glass bulb contains 0.1 molar HCl, look at it here, in the glass bulb, 0.1 molar solution of HCl, and a tiny silver chloride electrode. Look at the silver chloride electrode here. When the bulb is inserted into an acid solution, it behaves like a hydrogen electrode. It is used to measure in pH determination using a reference calomel electrode. So this is another type of electrode, the glass electrode, which is also used and can be used in reference to the calomel electrode to replace the standard hydrogen electrode. In conclusion, we've looked at electromotive force, looked at standard electrode potentials, looked at standard hydrogen electrodes, and looked at determination of standard electrode potentials using standard hydrogen electrode, looked at representation of cells, and also looked at the other standard electrodes, that is the calomel electrode, silver chloride electrode, and the glass electrode. Thank you very much, and see you in the next class.